Well, good afternoon. I'm going to get us started as usual. I think we're going to have our people trickling in. I told our speaker about that, but I'm glad all of you are here. Welcome back to the Wildfire Seminar Series for winter quarter here at Stanford. As you can see, it's obvious we are still on Zoom, and I guess be on standby. I'd hoped us to be live at some point this quarter, but I'm trying to be consistent with our university's policies, and Omicron numbers are coming down, so maybe we will be in Tree Run 104 in a couple of weeks. But for now, we are on Zoom, which makes it accessible actually to a lot of people in many ways. And of course, we will do Zoom even if we go live, so it will be hybrid. Just want to acknowledge again, we've had a lot of great partners supporting this series, including the Bill Lehman Center, the Woods Institute, the Priest Court Institute, and then finally, Stanford Sustainability Data Science. And just a big plug on my own behalf, we are doing this in conjunction with next quarter's spring quarter Big Earth Hackathon. And so if I know there's only a few students right now live in the audience, but those that are listening in later on, or if you know students who might be interested, please encourage students to check out bigearthhacks.stanford.edu to register for the event next spring quarter, and also note to them that there is a companion class where students do not have to, but can take a class for credit in conjunction with the Wildfire Hackathon. But with that being said, I am pleased that we have Dr. Jeff Mirocha in the house today to teach us a little bit more about what's going on the more research side of looking at wildfires. Jeff Mirocha is an atmospheric scientist in the Atmosphere, Earth, and Energy Division at the Lawrence Livermore National Laboratory, where he has spent 18 years working on a variety of topics related to multi-scale atmospheric simulation. Currently, Dr. Mirocha is leading a project to improve coupled atmosphere wildfire simulation capabilities to better understand fire spread, emissions, and potential mitigation pathways in areas of complex terrain and the wildland-urban interface. Jeff Mirocha holds a BS and an BA degree in geography and mathematics from Arizona State, and an MS and PhD degree from astrophysical, planetary, and atmospheric sciences from the University of Colorado at Boulder. I think you will be entertained and hopefully well informed by what Jeff shares with us today. And he's told me he's going to leave plenty of time for questions. So I hope for, again, a feisty and engaging dialogue after his formal presentation today. As usual, we got a small group. We'll be probably 20 to 30 people. So feel free to raise your hand or ask questions along the way, or if not, I will moderate things via the chat. Take it away, Jeff. I'll let you share your screen.
Okay. Echo test. Are we seeing a screen come across?
Yes, we do.
And are we in slide sharing mode?
Not yet. There you go.
All right. Thank you very much for the introduction. I'm really happy to be invited to present and talk to you. And I do hope that we do have a feisty exchange of ideas and thoughts. As Derek said, please, I do interrupt. I won't be offended. It's hard for me to monitor hands going up and things. So feel free to interrupt at any time if you have any thoughts or questions. I'm going to give more of a high-level overview of some of the research strategies that we've undertaken at Lawrence Livermore under a handful of projects that really started just a few years ago in response to the 2018 wildfire season. And I'm also looking to present sort of the key gaps that we've identified, attempts we've undertaken thus far, some high-level results, but also would love to get your feedback on whether you think these are the right things to be doing, and if they're interesting avenues for collaboration going forward, and if some of the data and methods can overlap in any way with the hackathon, that would be just wonderful. So with that as preface, let me start with my framing of the problem. Wildfires are definitely part of our future. The dream of not having wildfire in the landscape is over, and we now have to manage, mitigate, and coexist. But these are very complicated fires that are burning in very heterogeneous landscapes involving people and urban materials. This is a CAL FIRE video image of the Carr Fire, which was near Redding, California, burning down the mountain into the wildland urban interface. And you can see this rotating core. This was actually an EF3 scale tornado. There was lots of evidence of tornadic winds with overturned cars and twisted up infrastructure. This is a very telling image describing the role of the different scales of atmospheric motion, landscape fuel heterogeneity, fire physics that all come together to create these dangerous conditions. These are the kinds of conditions that we need to understand better, and observations like this are vital to enabling that understanding. However, we also need models because we can't, although we have some great remote sensing technologies, it's difficult to get close enough and at fine enough scale to really observe these kinds of fires in enough situations to be able to generalize physical relationships between fuels, fire spread, atmospheric state, how these all come together. So we're going to need models to do this. But how does one simulate something like this? We have a family of wildfire simulation models. They're very simple, highly parameterized surface fire spread models that run in 2D that just take sort of the atmospheric state, and they can propagate very quickly with various levels of linearization and simplification. Then we have sort of full chemistry, high resolution, physically informed fire spread models that look at the 3D structure of the fuels, the oxygen content of the air, and do the detailed chemistry. Now, you can't obviously run a high fidelity model like that at a scale that would allow you to investigate how would you protect this community? How would you fire harden? Are fire breaks an effective mitigation strategy? Can you slow the fire down? What kind of ingress and egress do you need to maintain for emergency services, evacuations, et cetera? So my view of this is that we need a coupled atmosphere wildfire simulation framework that can capture both the atmospheric inputs and responses to the wildfire spread in the aggregate scale that you can run on a large enough footprint to do landscape scale investigations of these things. But yet we also need better fidelity than we have today. And so what I want to talk about is how we're addressing the extreme complexity here of weather, landscape, fuels, and fire, or what I call our tentative path forward. So I want to introduce the idea of coupled weather and fire modeling, or atmospheric, multi-scale atmospheric simulation. As Derek mentioned, this for a long time, and maybe when your only tool is a hammer, the world starts to look like a nail. But I think there's a good motivation for the necessity of capturing these multiple scales of atmospheric interaction. The top image that I'm showing here is how we use a model. Here in this case, the weather research and forecasting. It's an atmospheric science or weather prediction model, process study model, widely used open source model that allows for this thing called grid nesting, where you can refine a subset of the computational domain to pick up finer scale, higher resolution features. Here's an example of a flow simulation we did. This is an Oklahoma City urban environment resolved at 2 meters with inflow from 6 kilometers. And downscaling, you can see that you pick up finer scales of meteorological variability and ultimately get these turbulent flows around the building structures. I think this is something that we've done in our wind energy context, with a little bit more the physical fidelity that you pick up. Here's a turbine or an array of wind turbines. They're yawing into the inflow direction, and here comes a cold front blasting through. Looks like a firewall. It's not. This is just the wind. But the idea is that you can couple across scales, and you can introduce physics in the same way that we've done for buildings and for wind plants. We can do the same thing for the fire problem. However, in the fire problem, I argue the complications are much greater and more numerous. And I'll go into a few details about why that is the case. So what can we do today? It's always a good idea to assess the current state of the art. This is a movie of a simulation of the Camp Fire near Paradise. It's several days compressed. And this shows essentially at a high level fire, winds, the landscape and the fuels all come together to feedback on the progress of this fire line as it advances down the mountain. So we have frameworks that can already do this at a fairly aggregated level, capturing essential physics and interactions. And if I drill down a little bit further and look at a cross section in the vertical plane here, this is from a different simulation using the WRF S-fire model. I have an S in parentheses here because there are different versions of the WRF-based fire models. S-fire is one, there's also a WRF fire. And so I just put the S in there parenthetically sometimes, but not consistently. But these are basically very similar modeling approaches. But you can see in the image on the right, you can capture the fire front advancing, the heat released in the colors here. You've got the wind barbs in the atmosphere showing the wind flow. You've got indications of smoke concentration. You've got updraft plume dynamics with the cloud microphysics. What you can't see as well, but is a really big part of the issue of getting accuracy in these simulations, is the state of the wildland fuels. What's there, how much of it, how wet is it? That really impacts how the fire advances. So where we are today and where we need to be, obviously, there's some fidelity gaps that need to be bridged. Some of those involve model numerics, surface fuels, the fire spread model itself, and some of the atmospheric integration. So I'm going to spend just a couple minutes on each of these topics, indicating what we're doing to try to address these gaps. So in this image, we show just a still frame of a fairly coarse resolution simulation, several hundred meters to kilometer scales. You can pick up some of the big canyons and ravines and mountain ranges. You don't get the fine scale canyon effects. And the atmospheric interactions with the surface fire are captured, but we can do a lot better. One of the issues with and other mesoscale models that people often use to capture the meteorology is that they use terrain following vertical coordinates. So this is a numerical implementation that's shown on the left here, which for many reasons in mesoscale forecasting, you like to have the coordinate surfaces actually follow the slopes of the terrain, and they smooth out as you get higher up in the atmosphere, as you can see happening here with these grid lines. This is fine when you're doing mesoscale prediction and you have such coarse resolution at the surface that your slopes remain pretty narrow, pretty shallow. But when you start resolving things at finer scale, you pick up these very steep terrain features, and the model numerics can't handle it. The model will start introducing significant errors at around 20 or so degrees and will not run past somewhere in the 30 to 40 degree slope range. So what we've done over several years at Livermore is worked on immersed boundary methods, which allow you to map the terrain as an immersed surface within a grid that has relatively flat coordinates that looks very Cartesian, and therefore you reduce all the numerical errors, well, not all of them, but the ones associated with the sloping terrain. This is an example of something that was done by a former Stanford alum who works at Livermore, Bobby Arthur, implementing immersed boundary methods and coupling them with topographic shading within the WRF model. And what you're seeing here, this dark gray front is the shadow front as the sun sets off in the horizon, and the blue contours are the wind speed component that is flowing downhill. This is a density current, right? When the sun goes down, the cool air sinks into the valleys and it flows down the hill. So we can do this now, this kind of thing in WRF that we couldn't do just a few years ago. And this is really important for wildfire because fires propagate in steep slopes. And we know that when the steep slopes get steep enough, the fire growth can become explosive. The rate of spread up the slope is much faster. Another thing that we can do with the same immersed boundary methods is simulate buildings. So what I didn't show you in the image before of the multi-scale simulation is that this urban area is actually implemented in the WRF model using the immersed boundary method. So these are actual three-dimensional buildings that are sticking up off the surface. So we have a numerical framework now to actually do fire spread on steep slopes and moving into urban areas. There's more to complete that capability, but this is the idea of using the immersed boundary methods, and we've made some great progress in that respect. One of the things we also need to work on is the classification of landscape fuels, because even if we have the best models, garbage in, garbage out. And we've developed some methods to use both satellite data and aerial imagery data combined with some machine learning techniques to try to recognize features of relevance and classify them in a way that the fire spread model can do a better job of propagating fire through these landscapes. Natural rotation challenge dead trees, for example, are difficult to differentiate from barren terrain. So when you've got bark beetle kill, your first guess at what the fuel availability is could be significantly off because you're counting these dead trees as bare soil. And we really don't have much to go on in the realm of urban materials, how to recognize different categories of combustibility so that we can propagate fire spread through urban areas, for example. But we're developing the framework to begin to piece the landscape fuel characterization together in both wildland and urban environments. I'll show a couple quick slides about that in just a minute. Another piece of this pillar is once you get the ability to do fire over steep terrain and you classify the fuel environment, you got to burn the fire through there. And so the chemistry and combustion characteristics of the fire spread models used in WRF-S fire, this basically goes back to Rothermel, mid 1970s. It looks at wildfire as basically a grass fire with different fuel densities. It's a fairly empirical, simple model. It kind of relates the ability of the fuel to convert and release heat to the sink of energy of getting the fuels prepared and the moisture content and things of that nature. It probably can be extended with the use of better information about how different categories of fuel combust and what they emit. It's maybe limited in the long view because it doesn't incorporate things like slope effects and other wind-driven forcings as well as some newer different models that are out there, but it's the most widely used model. And it's the model that we are working on improving as well using chemistry combustion models that, again, will show another slide that expands this a little bit. Then there's the output of the fire into the atmosphere and the feedback of the atmospheric state back onto the fire. And this can happen through heat release and convective air currents, but this can also happen through the aerosols that are emitted when fires burn and the interactions of those aerosols, both directly with radiation, so the dimming effect of shutting down the solar insolation, reaching the ground, but also when you have clouds around, you change the size distribution of the clouds, and that can change the microphysics in a way that feeds back on the fire. And so WRF also has a chemistry module where you can plug in the fire outputs, and getting the plumbing working in that has been another part of the project. But this is essentially where we are trying to move everything together. My last few bullets here on the fire spread physics. Ultimately, longer term, we're going to need better fire spread models. You probably know the fire lab at Missoula is working on improving a fire spread model for the wildland area. I believe you had a guest speaker last week from UC Berkeley who does the fire table simulations, Michael Gollner. There are lots of people working on this, and hopefully we'll get better fire models to stitch into these codes soon enough. And then there are approaches looking at, well, there's all this physics and that's great, but can we use machine learning? There are folks starting to work on machine learning-based wildfire spread models based on both observations and other higher fidelity model simulations. So, if nothing else, this framework for simulation could potentially dovetail with both providing data for machine learning-based methods and also utilizing those. So that's kind of the big picture of how we're trying to integrate these different threads into improving the WRF-S fire and similar mesoscale models. I want to spend just a couple minutes on a couple of the threads here and just a touch more detail that might be interesting to some of you. So characterizing the landscape fuel distribution using satellite-based imagery, we started to do this using the Sentinel, which is a multispectral data set that has nominally 30 meter, but down to 10 meter resolution available. And the idea here is to use the different bands in clever ways, using perhaps a number of hidden layers in a neural net or some other classification scheme to try to figure out where what you actually have covering the surface at any point in time and space, and potentially being able to use this data then to move into the wildland urban interface once you've sort of trained and validated on landscape fuels where you have good data sets to compare against. And we're still pursuing this. In conjunction with this, we recently obtained some higher resolution imagery data from airplane flights. So here's an example of a footprint of a small area showing a road and some rocks and some trees and some bushes, meadows, the sort of variegated landscape that you get in a lot of California. And the idea is that when you run WRF's fire spread model that's based on Rothermel, it requires a categorization of every pixel or every sort of model grid cell in terms of what kind of fuel is it and what is the state of that fuel. And these data sets often don't match changing conditions. So the imagery and the satellite data can help us time match things better, but also the coarse resolution can limit high resolution applications. So for example, if you were looking at building a fire break to protect an asset, or looking at forest thinning strategies to try to slow or stop fire spread. And so this road here for certain categories of grass fire, when there isn't too much ember casting, would probably stop the fire from spreading. But as you can see, the land fire fuel map on the right that the WRF model would use doesn't see the road. So these are the kinds of issues that we need to be working on, and we are working on, producing fuel maps that portray the current fuel conditions, and then seeing what the impacts of these are on our simulations. And here's just an example of how we're progressing through this landscape fuel characterization from the 1 meter aerial imagery using neural nets. We've undertaken some classifications and are working now on translating the characterization of the different surface cover types into data for the Rothermel model so that we can actually put this into WRF S-Fire and run it at high resolution and see if we can stop certain fires with certain preventative measures. So that summarizes what we're doing with the machine learning for surface fuel categorization. The next step I'd like to talk just a little bit more about is why we're using chemistry combustion models to better characterize combustion emissions parameters. So there are some assumptions in models like Rothermel regarding the simplicity of the complete flaming combustion that happens and the output of that type of combustion, which is black and brown carbon that's emitted. In reality, we know we have smoldering fires, we have moisture content affecting the output of not just heat and fire spread, but also the type of aerosols and chemicals, precursors that are emitted during combustion. So it's really critical for air quality and CO2 inventory analysis that we are able to better represent the chemistry that's happening from these landscape fires. And the way that we're doing that is using codes that are widely used within the combustion industry in terms of like vehicle technologies and things of that nature, but modifying those to work to classify the combustion emissions of a broader class of fuels, such as wildland fuels. So developing a multi-region CFD code that can account for the particle shrinkage, using the detailed kinetics to solve the gas phase chemistry. Then we can put these things together to study the various phases of combustion, char oxidation, all the way through the life cycle of the burn and the mass loss at the particle scale. And this will help us provide better parameters for this relatively simple models. But then if newer, better models come along, they're still going to depend on these kinds of fundamental combustion and emissions parameters. So that's the long-term vision for this work that is underway at present. And we're hoping for some results shortly that we can actually roll up into a publication on the impact of this. Going up a scale, when we talk about being able to improve fire spread predictions and interactions with the landscape, we want to be able to do risk assessment and protect infrastructure, look at resilience. Now, we have another project that's looking at trying to link climate forecasts of large scale change down to threat drivers for infrastructure, for people, in terms of what we expect to be happening with the changing changing climate. We all know the big picture, but people have real questions about where do I build the renewable energy grid that California is going to be investing in and building out for the next 10 years? Where do we locate critical water assets, for example? So I don't think I need to over-explain this to this audience here, but much of what I've presented is sort of at the bottom of this diagram here, using multi-scale physics models. This is great, but they're slow and they contain systematic errors. There's another effort to go to machine learning straight away. And if we can build associations between sort of coarse scale weather and local scale impacts on the terrain, can we go straight from climate forecasts down to the threat drivers through this upper loop of machine learning? So part of the objective of the multi-scale physics models is to validate and help build these machine learning models as well. So this is a bigger program with some overlapping and mutually synergizing thrusts. But the idea is to get information out at the end of the day, enabling us to better quantify risk and uncertainty and make decisions about where to put things and how to better protect them. So sort of summarizing the whole portfolio of our kind of project space, really our focus is of course largely on national assets. So here along the bottom are some pictures of fires that have burned through radioactively contaminated sites and or in or near actual national laboratory infrastructure. We also have had fires breaking out in the Chernobyl area. We have threats to infrastructure like grid. And then we have, of course, civilian impacts as well. So what these all have in common is a need to better understand the threat drivers, but also to better understand the efficacies of various mitigation pathways. How effective are these things? How well can we believe the models? How much do we need to improve the fidelity of the models to get to believability? So this is a cutting edge interdisciplinary science and engineering problem, lots of facets. We think open source codes and data sets and multi-institutional collaborations are the way to attack this problem. It's a big problem and nobody's going to solve it on their own. But it's a collective problem that we all have to deal with, and hopefully we can all pitch in, work together and get somewhere with this, because the world is relying on this input. So that's kind of the big picture. I have just a few closing of one particular project that we've undertaken that we're just about getting ready to publish the results on, and also that will provide sort of a backdrop for how much are we actually improving the models. So we undertook to simulate the summer 2020 Northern California complex fires that resulted from that giant lightning storm that rolled through and lit off numerous fires that converged into several of these mega fires, and I believe we even had the state's first gigafire up north at some point. And of course, these fires burned close to home, but they provided a pathway for us to assess the current state of the WRF-S fire model in terms of its ability to do fire spread, but also to look into emissions scenarios. I think we all remember that these fires weren't as deadly and harrowing as fires from previous years, but the smoke inundation was pretty horrible, and the health consequences of that smoke inundation are still being inventoried. And we'll probably never know all the details, but we know that it wasn't good. And we remember the orange skies, which were made for some beautiful apocalyptic photography. We simulated this entire sort of month-long event using the WRF-S fire framework with the grid nesting as shown here on the left, drilling down to 1 kilometer domain, 1 kilometer grid cell resolution domain on the inner footprint, which captured the complex fires near the Bay Area as well as the Creek Fire out east of Fresno. We set this simulation up in a few different ways. One of the ways that we did this was to use an inventory of emissions and a plume rise model that propagates the the emissions from the fires during real time without the need to actually burn a surface fire spread model. So there's the FIN, which is NCAR's sort of satellite model-based assessment of how the fire smoke entered the atmosphere, at what heights, at what times, and you can simulate that going forward over the month-long period. But the other thing that we did was we actually ran the surface fire spread model within WRF-S-Fire to compare the results. I'm not going to go through an exhaustive comparison here, but here's just a couple of timestamps, one timestamp on the top, and another one on the bottom showing PM 2.5. With the S-Fire simulated, so this is the setup that actually burned the surface fire, consumed the fuels, propagated the fire across the landscape on the left, versus just using the satellite-based emissions inventory. And a few takeaways from this is that the WRF S-Fire model produces significantly higher PM 2.5 near the surface in general than the FIN does. Secondly, if you look carefully zooming in, you can see some darker circles. These are areas where we actually had observations that we compared with. So for example, here's a place that's near and dear to our heart out in Lawrence Livermore Lab, our home. What's shown here is a time series going out for a few weeks of the entire, basically the entire period. The WRF S-Fire hooked to the chemistry produced PM 2.5 according to the orange line, whereas FIN emissions without burning the actual fire spread, just using the satellites, are these blue lines down here. And there are a couple of other, the data measurements that we use from the EPA are these filled circles, and these horizontal lines are just thresholds for health. And I'm not going to go through every detail here, except just point out a couple of high-level things. S-Fire tends to overpredict the surface concentrations, and the fire area tends to be too large. We're not sure exactly why that is, but we are investigating. We also, both of these frameworks missed the long-range transport from the Oregon fires that blew down into the Bay Area. So there's something about the regional circulation that also needs to be captured better for these sort of geographically dispersed fire smoke effects. But by and large, we have these data from about 30 or so of these areas, again, indicated all over the state. And we're publishing the aggregation of a lot of the statistics of how the different models performed. That'll be the data set. We'd be happy, you know, if there were people who wanted to look into these data sets to learn some things, or just think that there are collaboration pathways. We'd be very happy to discuss that. The other thing that we looked into a little bit, and sort of a science highlight that we're trying to put together on this, is that I think a lot of people understand that when there's a lot of wildfire smoke, it shades the surface, which shuts down the convection, which limits the dispersion of the pollutants upward and out of the boundary layer into the free atmosphere where they can blow away. So you get this sort of accumulation of high PM 2.5 near the surface. Well, that's true. In a climate like ours, where we're strongly influenced in the summer by these onshore intrusions of marine air, the delta breeze, right? It's driven by this temperature contrast. The hot interior valleys bring the cool air in from the coast. But if you shade the interior so that it doesn't heat up as much, you get a reduced onshore flow. And this can actually make the pollution problem worse. So we identified an interesting, another feedback. The other thing that we've been trying to tie this up into a little bit is that there's a lot of renewable energy being deployed and already in service in these areas, the Altamont and Solana wind farms, and discussions of more solar. We know that there's a direct effect of smoke on solar production, but what you're seeing here is the impact of wildfire smoke on actually shutting down a little bit of wind generation. So if you think about in the hot summer in the interior Central Valley, you get the smoke, right? So you shut down on your solar, you shut down a little bit of your wind, but you also may have more demand because people are running their HVAC because they can't open up their windows. And are you entering a sort of worst case scenario where you put a lot of stress on the grid? So there are so many different ways that you could take this work and branch it out. But I wanted to provide just a few kernels of things that we're working on So my charge to the group is, let's bridge the gaps. And I'd be happy to take any questions or comments that you have.
Well, thank you, Jeff. That was a really compelling talk and raises, I think, a lot more questions than provides answers, which is a really honest assessment of where we are. I'll open the floor up for questions. And Jeff, you got yourself on screen. So does it mean you have a question?
Yes, I do, Derek. Thanks. Jeff, thanks for that talk. It's great. As someone who's relatively new to this field, it's really helpful to see what's being done. And I'm delighted that Bobby Arthur, someone who I know very, very well, is working with you in this. That adds to my confidence in the quality of the work. So that's great. You didn't, a lot of the work you presented was on fuel-to-fuel transfer and land-based spreading of the fires, Rothermel and all that. But you didn't talk at all about fire spotting and the issues associated with sort of the, if I want to call it sort of the atmospheric based spreading of fire through spotting and dispersal of embers. How serious an issue do you think that is, and what is being done about trying to model that?
Okay, great questions, and definitely an oversight on my behalf to not at least mention that, because we've seen so many images now of urban areas where the trees are all there, they were nice and moist, and it's the buildings between the trees that are gone. Kind of the inverse image of what you would expect. We are not actively working directly on the ember casting and fire spotting. However, we feel like our combustion chemistry models can help characterize how those embers will decay and burn as they loft. And we understand that there are efforts underway from, for example, San Jose State, putting together some actual, Ellie Tuhidi just gave a seminar yesterday on this topic. So we're trying to leverage where we can make big impacts with our unique capabilities, and we're trying to build partnerships to bring in things like the fire spread model that could be integrated with the Warfast fire. And if we have an opportunity to use our combustion models to help make those models better, that's how we're looking to participate in that.
Great, thanks.
Other questions? I'll read off Bill's for now, and actually I have a related one if we keep going on it. So Bill wrote, I think, a little bit earlier. Actually, Bill, do you want to speak up for yourself? Elaborate on that? You have your comment in the chat.
Sure. Great presentation. I'm an old CFDer, so I apologize if this is in the weeds a bit, but when you showed I think you called it the immersed boundary simulation, that's a standard Cartesian interface with a geometrical surface, and those typically don't do viscous flows. So are your simulations viscous or inviscid?
No, they're viscous flows, and we have a sort of what we call a logarithmic surface interface. So there are a couple of different ways that we implement the immersed boundary. One is to model the shear stress at the surface so that the subgrid model then can do the stress divergence to get the accelerations to the flow. But the simpler immersed boundary method is just to reconstruct the velocity at the first grid point above the immersed surface based on a logarithmic extrapolation. So you're sort of using the log law as your surface boundary condition. I feel like maybe I'm not exactly addressing your issue, the issue that you raised, but no, we do turbulent flow simulations, and
so you're modeling the turbulence and you're capturing things like the Earth's boundary layer and the vortex separations from the induced fire fronts. And
so we haven't done fire with yet. We haven't looked carefully at what we have done is accomplish the ability of the Rothermel fire spread to move along an immersed surface. But we haven't studied yet the interaction with the atmosphere. But the actual flow simulations that we have examined with the immersed boundary methods do capture the Ekman spiral and the log layer near the surface, and the turbulence spectra look look reasonable.
Interesting. Okay. Sorry, I'm an airplane guy, so I may be asking dumb questions. Atmospherically speaking.
Yeah, you're capturing sort of a different boundary layer, I think, than we are in the atmospheric flow. So maybe that's it.
Yeah, but I've actually done work with aircraft in the Earth boundary layer, and it's a pretty significant effect. Start looking at the details of how things operate near a surface.
Well, if there are specific metrics that you think we should look into to evaluate our codes, feel free to shoot me an email and we can carry the conversation offline.
Okay. Yeah, we've done some building simulations and stuff, just that kind of stuff. Okay, thank you. Sorry.
Thanks for the question, Bill. Felicity, you're next.
Okay, well, I am totally impressed and a little bit overwhelmed because I don't come from a physics or a statistical or modeling background. But given that fire is an issue for everybody, and given at the same time that the state is facing incredible deficits in housing, and you said specifically that you're still working on how to model houses as fuel and different construction elements and things like that. At what point is your modeling going to be useful to people designing communities or to people fighting over whether or not if you build a community here, you're going to burn up my house?
That's just such a great question. And the models won't be ready soon enough. I think by the end of maybe in a couple of years, we'll be able to start providing some better guidance. I think we're close with these models. They need to be validated. But that's a really tough question. I think, the idea of, do we rebuild Paradise? Do we rebuild, some of these towns? And really that's a tough one. And I'm more of a physics modeler. I know that these are the applications that are calling on us to improve the fidelity of the physics models. I'm probably not the best person to give you a defensible timeline, other than we just all understand that that's the primary objective of what we're trying to do here. Sorry for that bit of a non-answer, but it's
No, it was an honest answer, and it's as long as everybody knows that's in some ways the most important utility of your models, and obviously they got to be good.
Yeah.
Thank you.
Thank you.
No, great question and a great honest answer. And again, I really appreciate the honesty. We like to be honest in this group to really show that we have a long way to go. Xiao Yang, you have a question?
I do see a hand up with a picture, but I don't see lips moving. I guess that's
Oh, she's coming on.
Yeah.
Okay, good.
Hi, I'm Dui Yang. I'm current PhD student from the operations group in the business school. So I'm sort of interested.
I think we lost you.
Hello, are you able to hear me?
We lost you for a second. Can you start again?
Hello? Are you able to hear me?
Yes. Try once more, please.
Eric, I don't think she can hear you. So.
Hi, are you able to hear me now?
Yes.
Okay. So I'm a current PhD student from the operations group in the business school, and
maybe you can type your question into the chat. It's just dropping in and out.
So yeah, well, let's let her type her question and I'll move to Arun, and hopefully Xiao Yang's question can come in chat.
Yep.
So Arun, do you have a question?
Yeah, I had a question. Thanks for your talk today. I really enjoyed it. I was just wondering, I might have missed this, but how are you planning to resolve the scales when looking at your, when coupling the atmospheric and the wildfire models, specifically with the cloud microphysics that you mentioned? Are you doing some sort of DNS treatment in the cloud region, or how exactly do you plan to address that?
Yeah, that's beyond. So the ultimate high fidelity requires resolution that's so fine that you just can't do a large enough area to examine sort of landscape scale impacts. So, there will still be lots of opportunities for CFD models to look at individual bits of fuel and aggregated, maybe how does a house burn? What we're looking at is a scale sort of between the fully resolved combustion chemistry and the two aggregated sort of climate scale footprint, of marching along in 4 kilometer square pixels, right? Because then you're not resolving anything. So interestingly, the models like WRF have parameterizations for physical processes that are usable at the kinds of scales where you want to resolve updraft plumes for pyroconvection, and the fire turbulence, not down to the Kolmogorov scale, of course, but at, I think we believe, a scale that can help us answer these questions about the wildland urban interface, for example. So that the existing microphysical schemes and coupled with the turbulence models are more or less in place to be examined in this context. And I'm sure we'll learn, we'll break some things, but fundamentally it's there, I think.
Got it. Thank you.
I see Xiaoyang joined us again, and I'm going to suggest that maybe you can speak without your camera on to save yourself some bandwidth, and maybe your question will come through.
Okay, sorry, my laptop is having some issues. I'm using my cell phone. My question is, I saw your model on simulating the fuel interaction with the fire, which is super cool. And I'm sort of wondering whether this sort of model have some implications on the long-term fire damage structures on certain lands, because I'm from the operations community, and I'm very interested in how this type of simulation models could interpret into the long term to help make decisions for plannings and stuff.
So do you mean in terms of I think this is similar to a previous question about if you're going to build or protect infrastructure, how do you assess risk and mitigate risk from wildfires and intruding into the built area? Am I understanding you correctly?
I'm more like particularly interested in, like, is there a current stand? Do we have for some functional form interreactions between for example, fuel load and fuel type and the potential fire damage in the long run? Do we have quantitative insights from these simulation models?
I don't think we have.
I'm not sure whether this makes sense in this context, but
yeah, I think I understand your question. You're thinking of a functional relationship that tells you, given the fuel state, the amount of fuel, maybe the fuel moisture, what is the probability that a wildfire will exact some type of damage to?
Yes, exactly.
I would say that that's another thing that the community is really working towards. And I think, there are groups that are doing work on evaluating structure, sort of resilience. I don't know if resilience is the right word exactly. Reliability of different, types of housing, this whole structure hardening and materials paradigm. Is that kind of what you're getting? If you have a functional relationship that you can trust about the amount of, heating that a structure is going to have to withstand, then you can make decisions on what to build, how to protect. Is that?
No, it's more like I'm very interested in current fires, especially in the forest. and how different interventions in the forest would impact future fire risk and damages. So I'm just
Okay, so
trying
like clearing
to-
away,
yeah.
using prescribed burns or other harvesting of slash and, you know, accumulated fuels on the forest floor, that kind of thinning of trees. Is that?
Yes, yes.
Yeah.
Yes.
Yeah, I mean, that's why we're doing what we're doing to begin to investigate those issues. We don't have any answers yet, because this is sort of, you know, stage setting and model building, but that's the idea of why we're doing what we're doing.
Oh, totally. Yeah, that's cool.
Any other questions from the audience? I've got a couple queued up here if we don't.
I have one. So you talked a little bit about how renewable energy could be like potentially harmed or less productive if they're too close to wildfires. So do you think that modeling should maybe in the future be used in the siting process of like solar and wind? And do you have any idea of what type of buffer zone that would entail to keep it, you know, keep this renewable energy safe and whatnot?
Yeah, I don't think it would be necessarily a buffer zone to protect the infrastructure as much as it would be how much grid integration, how much battery storage do you need to absorb kind of a worst case scenario, like, you know, the polar vortex shutting down the Texas, the ERCOT grid, you know, a couple winters ago, right? This cascading failures issue. So I think, you know, understanding the likelihood of smoke impacting solar plants and wind plants, and then also the likelihood of, you know, the coupling with other things like on during a heat wave, you know, do you have more grid demand, and what demands does that place on, you know, if you're using stored water, you know, like we do often in the West here for what we call sort of ancillary services. If you're, you know, you can dial in more electricity to the grid. It's a form of storage, right? You can hold the water up there, but you need water to do that, which means you need rain and snow. And putting this all together into kind of risk maps, I think is a really important thing to do. And the details, again, I'm long on dreams and short on details here, but that's how we need to be thinking about this.
Gotcha. And then one follow-up, which this might be, I don't think this has ever occurred. But you talked like about how, like, you know, wind gusts can obviously you know, help spread wildfires. Have there ever been any like studies on like if wind turbines like harnessing energy from wind has like de-escalated like wind gusts and helped contain like large wind gusts from spreading wildfire? But I know you said earlier in your presentation that a lot of like these strong winds happen on like mountains and very like complicated terrain. So is that kind of just not applicable?
I don't know of any examples, because as you said, you know, typically you build wind turbines over relatively smooth surfaces. Even if there are like hills around, you want to put the turbine on top of a hill because you get this you know, acceleration of the flow. But tall forests we tend to stay away from because of the friction. It slows down the wind. So we don't have many forest fires that have burned through where we've had operating turbines. I don't know if we've really had any. Grass fires in the prairie are kind of a different animal. We're not, you know, too worried about them. I don't know that anybody studied the impact of an operating wind turbine on a grass fire. I think, you know, they would maybe shut down the wind plant out of an abundance of caution, but my intuition is that it wouldn't bother the operating wind plant whatsoever to have a little grass fire whipping across the prairie underneath.
Gotcha. Thank you.
Any other questions? We're getting a little bit close on the end of time here, but great questions today. Okay, Joe, well then I get a chance to ask one. Jeff, and this probably isn't suited for what your group is doing, but one thing that I wonder about, given my lack of experience in this area, what is the state-of-the-art model in terms of coupling these larger scale weather patterns with the weather generated by the fires themselves? And I'm not sure if you've alluded to the fact that, you know, Wharf Chem, does that account for like these mini tornadoes that are created by the fire itself and the microclimate that they've created?
Yeah, so I'll try to parse this out for you a little bit. So the WRF model is an open source atmospheric science code base that can be used from global scales all the way down to turbulence resolving large eddy simulations. It has the subgrid physics and the physical forcing, radiation, clouds, land surface, all of that stuff. Into that model, we have implemented the fire, not us, but other groups have implemented fire spread along the surface in terms of Rothermel, and there are a couple of others in WRF fire. There's a model by Balby that's a little bit more sophisticated and not as widely used. And we're working towards better models. But the idea is that the fire generates heating and the injection of smoke that gets lofted into the atmosphere, and it can feed back on the winds. So you get lofting, you get a lot of heat released and convective mixing, so that brings more winds down. But then what do you do with the smoke that goes into the atmosphere? That's where the chem module comes in. You don't need WRF chem for everything. If you want to study sort of chemical transformation of aerosol precursors into aerosol products and what they do, if they loft up into the stratosphere or if they blow down wind, many hundreds or thousands of kilometers, you need WRF chem. To look at sort of regional smoke impacts, you don't need the full chemistry package. Some of the WRF microphysics schemes are aerosol aware, and so the aerosol microphysics and radiation impacts can be captured over, sort of part of the state of California type of scale. If you were looking at, for example, the creek fire and the pyrocumulus, you don't really need WRF chem for that. Am I answering your question at all?
I think so. And I guess the bigger question, which I didn't probably state very well, is where are we in the state of the art at looking at the weather generate? I mean, LES we think is great. In fact, Bob's on the call here, so he'd probably say LES theoretically should take care of it. Is there any validation being done? Because I know you talk to firefighters that look at these intense fires. They've never seen the sort of weather they're now seeing generated by the fires themselves. So
right,
how well are our LES models doing at tracking the weather generated by the fires and how that couples back to the bigger weather that really happens?
Right, and that's a very difficult LES problem because the grid cell spacing to capture turbulence needs to be pretty fine, but the footprint of the whole model domain to capture the entire pyrocumulus needs to be really large, and you get into a big computational bottleneck. There hasn't been much done in that area yet, but I think, Neil Leroux at University of Nevada, Reno has probably done, is he still at UNR? I think he still is. No, yeah. There are some people who have compared LES to like LIDAR and radar observations scanned through fire plumes and have been able to capture, some smaller scale vortices. But, we're not quite able to do an entire pyrocumulus at LES scales, at least not where a traditional LES, a surface layer LES of, requiring 10-meter grid spacing, for example. Now, some people who do cloud, resolved cloud turbulence kind of stuff, they consider, 500-meter grid spacing to be LES. So
all in the eye of the beholder, right? What LES is, unless I think we all agree on DNS, so we're okay with that. Right?
But I think WRF fire is a great code. It's kind of, WRF is starting to age out a little bit in terms of being a modern HPC compliant code. There are people who are trying to put it on GPUs and doing different things with it, but maybe to do that scale of a problem, we need to be thinking about some new exascale focused codes that maybe aren't quite there yet, but that's maybe required for that scale of problem.
Well,
I think we can look at the near field using LES, but yeah, putting it all together is still going to be a little bit bootstrappy.
Yeah, we need a lot more computational horsepower for sure too, right? So
yeah.
Anyway, well, thank you for your time. Thank you for everyone sticking around. We're actually beyond time here, but thanks again to Jeff for just a really great talk and creating a lot of questions and discussion here. And I'm sure if you have any follow-up questions, I can put you in contact with Jeff. And Jeff, again, thank you for your time. And I'll be in contact with you a little bit in the next couple of weeks to see if you have some things we can put together for the hackathon to propose for students to work on.
Sounds great. Thanks to everybody.
Okay, thank you, everybody. Have a great afternoon and see you again next week. We have the Red Cross coming in.